Hello, and welcome back to the Cedille Caste. This video finishes the sequence on generically deriving induction for Mendler-style lambda-encoded data in Cedille. The first video of the sequence introduced the notions of F-algebras, Mendler-style F-algebras, and the fixed points of functors derived of them. The second video utilized the Cedille idiom monotonic, a predicate of positivity for type schemes that generalizes the notion of a functor, and gave the definitions of a P-proof F-algebra for dependent eliminations and the generic constructor for data types that will support an induction principle. It is recommended that you watch these two videos before watching this one. In this video, we finish our attempt to define the induction principle and generic destructor out by introducing a type of augmented inductive hypotheses. We will take our non-inductive fixim, rebuild it with the generic constructor for inductive data, show that the rebuilt data is equal to the data we started with, and show that the property we wish to prove holds for this rebuilt data. First, let us recall some definitions from the previous video. We saw before proof algebra, the type of inductive reasoning, parameterized by a carrier x so that it may be used with both fixim and endim, a property P of kind x to star, and an algebra in of type f of x to x so that it may be used with both in fixim and in endim for any type R for which we have a cast to x, and given an inductive hypothesis which takes any term of type R and produces a proof that P holds for R after we cast this R to the type X. And given R's some unfolded data of type F of R, we return a proof that P holds for the n of casted R's. So this cast converts this f of r to f of x, and then we apply n to get a term of type x. We also saw inductive m, a predicate indicating that some x of type fixim supports an induction principle, which is to say, given some property p of fixim, and given a proof algebra proving p with carrier fixim and algebra nm, it is possible to prove that the property P holds of x. End-M is the type of fixim data which are also themselves proofs that they support an induction principle, inductive M. To fixim is a cast from the inductive data to regular data, and in end-M is the constructor for data which supports an induction principle. Given some f of end-m, apply the generic collection of constructors to produce end-m. Next, we recall where it is we got stuck proving the induction principle. For any property P, now over our inductive data, see here, now that we are using a proof algebra whose carrier is end-m and whose initial algebra is in end-m, we know that D is formed by an intersection where the second component supports proof by induction. But unfortunately, this proof principle is too weak. It allows us to prove properties of the kind fixim to star, but the property that we have been given has kind ind-im to star. Therefore, we need a way to transform a property P of kind ind-im to star into some P prime of kind fix-im to star, such that a proof that P prime holds for D.1 gives us a proof that P holds for D. Let us define a lifting of properties from ind-im to fix-im. This lifted property is a triple. The first component is some inductive data ind-im. The second component is a proof that this inductive data is equal to the fix-im that we are trying to prove a property for. And the third component is a proof that P holds not of Y, but of X, casted using our equality to the type of Y. Now, let's see how we may use this to augment our inductive hypothesis. Define the type of augmented inductive hypotheses as a type parameterized by some carrier R, some type R, which is castable to fix-im, and a property over our inductive data ind-im, as a function, dependent function, taking arguments of type R, named little r, and returning a proof of the lifted property holding for R after casting this to the type of fix-im. Intuitively, what we will want to be doing is making an inductive hypothesis where each time we are returning this triple. The first component will be constructed by rebuilding our subdata. This is our subdata, with the inductive constructor in ind-im. The second component will then amount to a proof of an instance of the reflection law, that iteratively rebuilding the data with constructors produces the same data. This rebuild data is equal to the data we computed it from. The third component is the part corresponding to the proof returned by an ordinary inductive hypothesis. We will want to define two utilities for IH+, a Caste extraction and proof extraction. The Caste extraction makes use of the fact that the second component of our triple tells us that the first is equal to the subdata we were given. That is, we have for all R of type big R and all C, C's which are casts from R to fix-im, we'll have that the first component of our augmented inductive hypothesis is an ind-im, and the second component of our triple is a proof that the first component of our triple is equal to R itself. This allows us to form a cast from R to IndM. So given such an R, and a cast, and a property, and an inductive hypothesis, we must introduce a cast. The first component of a cast is just a function from R to IndM. This we get by taking the first component of our triple, the triple being produced by invoking the inductive hypothesis on the subdata. The second component is a proof that this function is extensionally equal to an identity function. But we have this already because that is exactly the proof given to us in the second component of our triple. Proof extraction just gives us the induction hypothesis we were originally interested in from the augmented inductive hypothesis for all little r of type R, P of R, after casting R via cast IH plus to IndM. For all subdata, the property we wish to prove holds the property we wish to prove of the subdata holds once we cast that subdata to the appropriate type. But of course, this is exactly the proof given to us in the third component of the triple returned by our augmented inductive hypothesis. Now, we need a way to convert a P-proof F-algebra to a lift P-proof F-algebra. This is where we will be implicitly proving the reflection law. For every property P of over IndM and a proof algebra over IndM with initial algebra in IndM, convert this to a proof algebra with carrier fixM property lift P and initial algebra in we assume this P and this alg, and then if we are expected to return a proof algebra M, then we are allowed to assume some R, some C, a Caste, an inductive hypothesis, and subdata. We have in our context a Caste from R to fix MF, we can use this to define a Caste from R to indm. By combining it with our inductive hypothesis, which, as it turns out, has exactly the type of IH+. Well, modulo some module parameters that are not needed to be given explicitly. In order to return a lift P of the constructed x's, we will need a triple whose first component is some indm, which is equal to nmx's. We can do that by first constructing an f of indm from x's. X's is our subdata, now casted to indm by utilizing the cast we just defined and invoking the monotonicity property of F. Finally, we can define an ordinary inductive hypothesis by using our proof extraction on the augmented inductive hypothesis. This means we are now able to return the triple. Again, the first component is some inductive data. We can easily construct this from x's prime. The second component is a proof that this rebuilt inductive data is equal to the constructed data from x's with the non-inductive constructor in. But of course, we recall from the previous video that in indm and in are definitionally equal, and x's prime is equal by definition to x's, because x's prime is defined simply by casting x's to a different type. So the required proof is simply reflexivity. Finally, we must give a proof that P holds of the constructed x's. Again, this is definitionally equal to P of in indm x's prime. This we get by invoking the proof algebra we assumed in the first place. Its first argument must be a cast from R to INDIM, which we defined already. The second argument is an inductive hypothesis, which we defined already. And finally, the third argument is some unfolded data to run the algebra on, which we have by assumption. After all that, the induction principle is straightforward to prove. Given a property P, a proof algebra, and some data, we just project out the third component of our triple after invoking the proof principle of our data on the converted algebra. Finally, we are able to define outM, the destructor of data, by invoking the induction principle. We will invoke it with a motive, non-dependent motive, that simply returns f of INDIM. The algebra assumes some type R, some Caste from R to INDIM C, an inductive hypothesis which we will not need, some subdata. We will simply cast, using monotonicity, the subdata to the appropriate type. This concludes the video. Thanks for watching, and see you in the next one.